In this video, we're going to continue to learn about hypothesis testing. We're going to learn about three types of tests. There's a two-tailed test, a left-tailed test, and a right-tailed test. A two-tailed test is when the alternative hypothesis is p is not equal to some number. So the null hypothesis is p is equal to maybe 0.2, and the alternative hypothesis is something like p is not equal to 0.2. Now, when you have that p is not equal to a number, that means the number could be greater than 0.2 or less than 0.2. So that means you're going to be looking in the two tails, the left tail and the right tail. Recall that the level of significance alpha is the percentage of times that you're going to reject the null hypothesis, and that's living in the tails. So since there's two tails, if alpha is 5%, that means 2.5% or half of alpha is in the left tail, and 2.5% is in the right tail, half of alpha. There's going to be a z-score that tells you when you're in the tail or not. So you're going to have a negative z-score that corresponds to the left tail and a positive z-score that corresponds to the right tail. In the past, 68% of a garage's business were repeat customers. The owner of the garage samples 200 repair invoices and finds that only 114 of them were repeat customers. Test at the 1% level of significance whether the true proportion of all current business that's repeat customers is not 68%. So when we say test at the 1% level of significance, that means alpha is 1% or 0.01. And I have a note that says z-scores corresponding to this particular alpha is z is equal to negative 2.58 and z is equal to 2.58. How did I find that? So let's talk about those z-scores first. Now we said a 1% level of significance is like a 99% confidence interval. So we want to reject the null hypothesis only 1% of the time and fail to reject the null hypothesis 99% of the time. So if we reject 1% of the time, then 0.5% of the time we're in the left tail and 0.5% of the time we're in the right tail because those two numbers add to 1%. So we need to find the z-score. You can find the left z-score or the right z-score. Either one is fine because the other one, so if you find the left one, it's just the opposite of that one. So if the left one is -3, the right one is +3. And if you find the right one, if you find that it's 3, the left one is -3. So it doesn't matter which z-score you find. So I'm going to find the right z-score, the positive one. And how I do that is I'm going to look in my z-table and I'm going to look for 0.995, not 0.99, 0.995, because the z-table tells me everything to the left of my z-score. And everything to the left is the 99% and the additional 0.5%. You could also go into Microsoft Excel and type equals norm.inv 0.995, 0, 1, and you'll get 2.58. So that right z-score is 2.58, which means the left score is negative 2.58. The other option is you could put in Microsoft Excel equals norm.inv 0.005, and that will give you the left z-score, which is negative 2.58, and so the right z-score is 2.58. Now let's write our hypotheses. The null hypothesis is that 68% of a garage's business were repeat customers. This is the assumption, so P is equal to 0.68 or 68%. The alternative hypothesis is told to us in that last sentence with the 1% level of significance. It says, test whether the true proportion of current business that's repeat customers is not 68%. Not means not equals to. Now our next step is to figure out if we have a large enough sample. The next thing we need to do is figure out if our sample is large enough. Is it large enough to conduct this hypothesis test? To check this, we're going to take n times p and n times 1 minus p and see if both of those numbers are greater than or equal to 10. So p here is 0.68 times 200, I get 136. 1 minus p is 0.32 times 200, I get 64. Both of those numbers are bigger than 10, so the sample is large enough. My first option is I can build a interval around the true p, and then what I'm going to do is see if my statistic lives in that interval. So I'm going to take p, 0.68, and I'm going to add and subtract 2.58 standard deviations. So the standard deviation is equal to the square root of 200 times p times 1 minus p, the square root of that divided by 200. And then I multiply that by 2.58, and I get my margin of error, 0.085. Please double check these calculations. It's important that you can get the same numbers because you're going to have to do this on the test. Then I take that 0.085 and I add it and subtract it to that 0.68 in order to get that confidence interval. And I get 0.595 and 0.765. Double check that you can get the same numbers. Now let's find p hat. P hat is the statistic based on the sample. P hat is 114 over 200, which is 0.57. And we're going to see if that 0.57 lives between those two bounds of 0.595 and 0.765. It does not. It lives in the left tail, which means there's sufficient evidence to reject the null hypothesis. If the null hypothesis was true, then 99% of the time, any statistic we get from a sufficiently large sample will be between these two numbers. It's very, very unlikely to have a sample with a statistic that's outside of these bounds. The chance of that happening is 1% or 1 out of 100. So that's highly unlikely. And guess what? We got something that was outside of those bounds. So this provides evidence to say that the true p is not 68%. So there's sufficient evidence to reject the null hypothesis. In the context of this problem, there is sufficient evidence to suggest that the true proportion of all current business that's repeat customers is not 68%. Now let's try this a second way, which is to find the z-score that corresponds to our statistic p hat. To find the z-score, we're just going to take 0.57, subtract it from the p, the 0.68, and divide by the standard deviation. That tells us how many standard deviations this p hat is away from the mean. Double check that you can get the same answer. I got negative 3.33. So we said that satisfactory statistics are between negative 2.58 and 2.58. If we get something lower than negative 2.58, we're in the left tail. And if we get something higher than 2.58, we're in the right tail. It looks like we got something lower than negative 2.58, so we are in the left tail. So we got the same answer. We're in the tails, so there's sufficient evidence to reject the null hypothesis. There is sufficient evidence to suggest that the true proportion of all current business that's repeat customers is not 68%. Whether you use the z-score method or the interval method, you're going to get the same final answer, which is to reject the null hypothesis. Now we're going to talk about a left-tailed test. What is a left-tailed test? That's when we only care about the left tail. How we know we have a left-tailed test is the alternative hypothesis. Remember that in a two-tailed test, we had the not equal sign. Here for a left-tailed test, we have less than. So for example, the null hypothesis would be something like p is equal to 0.2, and the alternative hypothesis would be p is less than 0.2. So we only care about the left tail. So if we only care about the left tail and we have a 5% level of significance, that means 5% of the time we're going to reject, and that 5% will be only in the left tail. So with a two-tailed test, if we had alpha is equal to 5%, we would divide that in half because we had a left tail and a right tail. So 5% divided by a half, 2.5% of the time we were in the left tail, and 2.5% of the time we were in the right tail. Because we don't care about the right tail, we're going to put all of that percentage, all 5%, into the left tail. So there's going to be one z-score that we're interested in, which we're going to call the critical value. That z-score is going to be negative And in a left-tailed test, we just need to see if we're less than that particular z-score. Now, in a right-tailed test, the alternative hypothesis is p is greater than some number. Maybe p is greater than 0.2. In a right-tailed test, if alpha is equal to 5%, that 5% is all in the right tail. So we're going to have a critical value, a z-score, that's going to be positive because we're on the right side of the mean, and we're going to see if we're bigger than that z-score. So let's look at an example of a right-tailed test first. So a college professor claims that 30% of Mount Holyoke College students own pets. You believe that the true percentage is higher. You create a sample of 90 students and find that 38% of the sample has pets. Test at the 5% level of significance whether the true proportion of students who own pets is more than 30%. Let's start by finding the hypotheses, because the hypotheses will tell us whether we have a two-tailed test, a left-tailed test, or a right-tailed test. So the null hypothesis is the claim that 30% of students own pets. The alternative hypothesis is told to us in the last sentence. It says test whether the true proportion of students who own pets is more than 30%. So here are the two hypotheses. And the next thing we need to do is figure out if we have a sufficiently large sample. So we're going to take the sample size of 90 and multiply by p, which is 0.3. And we're going to take the sample size and multiply by 1 minus p, and see if both of those numbers are bigger than or equal to 10. So the sample is large enough and we can continue. Now this is a right-tailed test. This is told to us by the alternative hypothesis. And in the last sentence of the problem, it says test at the 5% level of significance, which means we want to reject the null hypothesis 5% of the time, and 95% of the time we do not reject. So we need a z-score where 95% of the data is to the left of that z-score and 5% of the data is to the right. How do we find that z-score? We're going to look at the z-table and look for 0.95 and find the z-score that corresponds to it. Or you could use Microsoft Excel. So check that you can get the z-score is 1.65. Next, we're going to find the z-score that corresponds to that 38%, that statistic p hat. To find that z-score, I'm going to take p hat, I'm going to subtract p, and then I'm going to divide by the standard deviation. So double check that you can get the same value that I got, which is 1.66. Now 1.66 is bigger than 1.65. It's just a hair bigger, just a little bit bigger, but it is bigger, which means I'm in the right tail. So we had to check to see if, because this is a right tail test, we want to see if our z-score is bigger than 1.65, and it is. So there's sufficient evidence to reject the null hypothesis. In other words, there is sufficient evidence to suggest more than 30% of Mount Holyoke College students own pets. Now we said that we'll never know with 100% certainty if the true p is 30% or if p is actually greater than 30%. But if the null hypothesis was true, what is the probability of getting a z-score as extreme as 1.66? What do I mean by as extreme? I mean getting a z-score of 1.66 or higher. Another way to say that is, if I go out and create a sufficiently large sample, what's the probability that 38% or more of that sample will have pets? So this is just finding the area to the right of the z-score 1.66. Now our z-table gives us the area to the left. So we can find the area to the left and subtract it from 1. And if you do that, you'll get 0.048, which kind of makes sense because we said that 1.65 corresponded to 5% to the right, and 1.66 is just a little bit above it, which means there's a little bit less area to the right, and the area is about 4.8%. This is known as the p-value. If the null hypothesis was true, there is a 4.8% chance of selecting a sample of Mount Holyoke students and finding 38% or more of those students have pets. This is highly unlikely. It's below the threshold of 5%. So if our p-value was actually bigger than 5%, that would mean we'd fail to reject. If our p-value is below 5%, then we reject the null hypothesis. Let's try one more problem. A newspaper article claims that half of all children don't get enough sleep. Suppose a pediatrician believes the true percentage is lower. He randomly selects 400 children, and he finds that 190 of those children did not get enough sleep. Test at the 10% level of significance whether the true proportion of children who don't get enough sleep is lower than 50%. Pause the video and see if you can come up with the null hypothesis and the alternative hypothesis. So the null hypothesis is p is equal to 0.5, half of all children. And the alternative hypothesis is that the pediatrician believes the true percentage is lower. P is less than 0.5. Next step, see if you have a sufficiently large sample. So our sample is large enough. Notice that the p is 0.5 and 1 minus p is 0.5. So we can just take 0.5 and multiply by 400 and we get 200. So n times p and n times 1 minus p are both bigger than or equal to 10. So the sample is large enough. So we're doing a left-tailed test. 10% significance means 10% of the data is to the left of the z-score. What is the z-score? Z is about negative 1.28. And our goal is to take our statistic, find the z-score that corresponds to that statistic, and see if we're below the critical value. Now, in the last example, when we were doing a right-tailed test, we were seeing if we were above a value because that was in the right tail. Because we're doing a left tail, we need to see if we're below this critical value. So let's find our z-score. We need to find p hat, which is 190 over 400. 190 over 400 is 0.475. Then we're just going to plug that into the z-score formula. Double check that you can get the same thing I get, which is negative 1. So our critical value was negative 1.28. Negative 1 is bigger than negative 1.28. So visually looking at this graph that we have on the right, the negative 1 is to the right of negative 1.28. Because it's to the right, that's in the spot of the graph where we fail to reject. If it was something smaller than negative 1.28, like negative 1.3, then we would reject. Because we're on the right side, we fail to reject. So left-tailed test, when we're below our critical value, we reject. But in a right-tailed test, when we're above our critical value, we reject. Now let's find the p-value. If the null hypothesis was true, what's the probability of getting a z-score as extreme as negative 1? What do we mean when we say as extreme as negative 1 in a left-tailed test? Extreme means negative 1 or lower. So we need to find the probability of getting z is equal to negative 1 or less than that. So we just go into the z table and we look for negative 1, and we should get about 0.159. And that's everything to the left. Because we're working with the left side, then we just take the value from the z table. So this is our p-value, 15.9%. Notice that it's bigger than the threshold of 10%. Our threshold alpha was 10%. This is 15.9, which means we fail to reject. If the null hypothesis is true, there's about a 15.9% chance of selecting a sample of children and finding that 47.5% or less of those children don't get enough sleep. Because 15.9 is larger than the threshold of 10%, we fail to reject.